Hi, everyone. Today is a very special day. We have a very special guest of honor. Today, we are joined by Dr. Bharat Ratra. Dr. Bharat is a distinguished professor of physics at Kansas State University. He's one of the leading voice in research related to cosmology or modern cosmology. He's known for his foundational work on dynamical dark matter and dark energy models. He was also selected for the American Physical Society 2025 Julius Edgar Linfield Prize for recognizing for both his contribution to physics and for his ability to communicate it. And today he will tell us about the story of our universe. So, Bharat, welcome to the show.
Thank you. Very nice introduction.
Thank you so much for being here and taking the time to talk to us at Texas Southern University. In fact, one of the ways to start the discussion, usually I prefer, is to ask people about what did bring them to physics. So usually some people had stories from their childhood or from their undergraduate, but when did you feel like you want to study physics?
Well, so I've liked building things when I was a kid. And I was probably more interested in engineering. And so when I went to college, I tried to get into an engineering program, but my entrance exam scores were not great enough, and I got into physics. And then when I improved my grades and they allowed me to transfer to engineering, I no longer wanted to because I was finding physics much more interesting. So probably when I was 18, 19, somewhere around then, I got really interested. I was interested in physics in high school too, but I was interested in a lot of things.
So you start as an engineering major or want to do an engineering, but you start for studying physics first.
Yeah.
As a way, and then you find yourself in physics, you find your passion in physics.
Yeah.
That's very interesting. And what brings you to cosmology?
So I was interested a lot in quantum mechanics, and I was interested a lot in general relativity. And I guess that eventually led me to cosmology because you have to do quantum mechanics and general relativity to understand cosmology.
That's so nice, like the idea of how the universe works, basically.
Yeah.
Everything around us work. That's great. Actually, it's a different story every time that question being answered. Every one of us has his own picture about how did we come to physics. But I think the one thing that makes all of us goes into study physics is that we want to know more.
Yeah, I'm kind of curious, I guess, and I'm really interested in what's happening around us. And it looked like cosmology was an area that hadn't been as much explored when I had my chance to choose what I wanted to work in. And so that's probably part of the motivation. I could see there was going to be lots of good data coming in. And it always helps to have great measurements when you're trying to do physics.
And I think you told me that you did your PhD as string theory, first.
Yeah, I started out in string theory and quantum cosmology, and then I got a postdoc in string theory. But I mean, it's really, really beautiful in mathematics, and I wanted to, I guess, do something that could be measured before I died, and I could see.
It's very interesting, so sometimes we have this beautiful theory that never been tested. So it's like we want something that we can capture in our hands.
Yeah.
Those ways. That's very interesting. Which brings me actually to the topic. When I was thinking what the title of this episode from our podcast Beyond the Equations will be, and I found like it's basically the story of the universe. How the universe evolved to the modern days.
Yeah.
And to a cosmologist like you, for a person that work with, try to put a model to describe our universe. How you imagine this universe started? What was the story from beginning? How can you tell it?
Well, we can't go all the way back to the beginning because we don't know what happened, but the universe is about 13.75 billion years old now. And we can go back to maybe when it was 10 to the minus 33 seconds old. And then a lot of people think something called inflation happened, where the universe expanded. I mean, the universe has been expanding all along, but it expanded very, very rapidly and got large very, very soon. And inflation hasn't been experimentally established at this point, but a lot of the predictions it makes agree with what we can see with our measurements. But our measurements haven't got to the point where they're precise enough to really constrain inflation.
Mm-hmm.
So after inflation, things cooled down, and the universe kept expanding, and then we created matter and radiation, electromagnetic radiation, and you had a lot of interactions. And at some point, when the universe was maybe a few seconds old, we had a bunch of protons, that's particles in nucleus now, and electrons and electromagnetic radiation. The quantum version of that is called photons. And the protons and the neutrons started fusing together to form the light nuclei, like hydrogen and deuterium and tritium and helium-3 and helium-4. And that part's been much better studied, and we can study stuff even a little bit earlier than that in great detail.
I think that's basically when we start speaking about, when the forces get to be separated and the interactions, that's what we can test in the modern accelerators today. Like Large Hadron Collider, we can speak about how particles gain mass by interaction with Higgs boson, or we create the quark-gluon plasma, the matter that created at the first beginning or the fraction of a second there. And then, as you said, the universe expanding, but what's actually expanding?
So that's a little difficult to get a handle on. So what's expanding is space itself. And I mean, Einstein, well, if you go back and think about what's driving the expansion of the universe, with a little bit of work, you can figure out it's the gravitational force that's responsible for that expansion, because it's happening on extremely large length scales. And on those length scales, gravity is the only relevant force. And the best model we have for gravity now is called general relativity, which was developed by Einstein. He started out with special relativity, where he didn't deal with acceleration. And then that paper was in 1905, and then 10, 11 years later, he had his first working model of general relativity. And there, unlike what happens in Newtonian physics, so Newtonian physics is the physics pretty much of everyday life, of stuff that happens around us on human scales, and even somewhat larger and smaller scales. But when you get to much, much smaller scales, you have to generalize Newtonian physics to what's known as quantum mechanics. And when you go to much, much larger scales, you have to generalize it to general relativity. And what general relativity does is it also includes space and time as two of the dynamical things in physics. As far as Newton was concerned, space was fixed and time ran uniformly, and everything happened in this fixed space. If you were dropping an apple, that would fall in this fixed space and time would run uniformly. And Einstein figured out that he could provide a better, a more accurate description of reality in certain circumstances than Newton could. And those were, in particular, circumstances where things were moving very, very rapidly at high speeds, or on very large length scales, or in very strong gravitational fields. And what he did was he said, I'm going to make space and time be part of the dynamics. So as the apple's falling, it'll deform space and it'll change how time runs. And so in general relativity, when you apply it to the universe, what's happening is that there's more space being created in regions where the density is a little bit lower than average. And that space spreads out, and everything lives in that space. So the galaxies live in it. And so as that space is spreading out, the galaxies get taken along for the ride. And that's what we're seeing. We're seeing that effect. The galaxies are moving further and further apart.
So if we want to break it down to the audience, basically we start with Newton picturing this as a box of 3 dimension, the space, and basically everything happening in flow of time inside that box.
Correct.
However, Einstein come and say, no, that's a 4 dimension. The time is part of that box. It's not separate, just something that's run by. And gravity is a distortion or an eruption in that space and time together.
Yeah.
So time comes to the equation as one of the dynamical parameter at that moment with Einstein.
Yeah. So that's the general thing. So you live in this 4-dimensional object, which is called space-time, and time and space both change. But for cosmology, the change in space is the more interesting part for the expansion of the universe. So you look at what's happening at different slices of time, and you can see how space looks different. And so it's in other systems, if you're dealing with a black hole, then there's a more direct relation between how time deforms and how space deforms. And you have to think about it a little bit differently. So the problem is this picture applies on extremely, extremely large length scales. I mean, so it's on scales where if you traveled at the speed of light, you'd have to travel for 10 million years or so before you start seeing significant effects. And
I think you told me before the podcast that basically we're not speaking about space expansion in our galaxy. You cannot see that in our galaxy.
Yeah.
It has to be between galaxies. So
you have to be between galaxies. You have to be on scales of tens of millions, hundreds of millions of light years.
I watched one of your lectures when he was explaining that, and it was very nice. You start with a picture of Einstein compared to the Earth, and you say like you need a couple thousand Einstein to have the Earth's diameter.
Almost 6.5 million.
6.5 million Einstein. And now we can imagine for between the Sun and Earth, we need how many million Earths?
Something like 70 billion Einsteins.
Yeah, to fill the Sun. And then imagine now we're speaking about the entire galaxy. How big is that? It was a nice analogy. I'm really advising our audience to take a look at that lecture. I will put its link in the description of our podcast as well. They can enjoy that. But since we're talking here about the expansion in modern days, but in the beginning, when everything was small, what drive that expansion? Do we have any kind of understanding about that?
Okay, so we have to be careful when we say everything's small, because in the simplest model that's consistent with the observations, space was always infinite. And what's happening as you go back is all those points come closer and closer, but it's still infinitely spread out in space. You have an infinite number of points in an infinite space. But what's happening is every one of those points moves away from every other of those points, and that's the Big Bang. So what's driving the expansion early on, during inflation, I guess that's your question, right? So during inflation, people think there's something a little bit like the Higgs field, but it's a scalar field, so so the temperature is sort of a scalar field. Like the temperature in this room varies depending on where you measure it. So closer to you or me, it's going to be a little bit higher, but some other place, it's going to be slightly different. So if you know where you are in space, and it's a 3-dimensional space, you have a vertical axis and 2 horizontal axes. So you need to know those 3 distances, and then you can get the temperature, and you can create this map where it tells you the temperature at each point in this room. And that's like a scalar field, but it doesn't give you the whole picture. And what you have to think about is what happens as a function of time. So when there's nobody in this room at night, the temperature will be a little bit lower because we're emitting heat. And so the temperature at that time will be smaller than the temperature at that same point in space now. So the temperature depends both on time and space. And it's just one number at each of those points. And that's what a scalar field is. At each point in space-time, it's one number. And the Higgs field is like that. And we know the Higgs field exists because it's been discovered at the Large Hadron Collider a little over 10 years ago, I think. And so the postulate was that there's another scalar field like that, but it's not going to be as massive as the Higgs field. It's going to be much, much lighter. And so if you think of the mass as being potential energy for the Higgs field to oscillate in, then this potential is much flatter. And so it has some energy density associated with the height of the potential, how high the hill is. But that hill is got a very, very gradual slope. And so as the universe or the scalar field moves along that hill, it feels the height of the hill. And because Einstein told us E is equal to mc squared, there's the mass there. And that mass acts as a source for the gravitational field that drives the expansion.
So in a different way, we expect a gravitational field similar to the idea of Higgs field. So it's a scalar field, meaning it has different point in different value in different space-time. And that what will be driving possibly the initial expansion of our universe.
During inflation.
And, that's very interesting. Also, one of the main points that you said, and I want to stress on it, is the idea that the current model is saying that the universe starts infinite in size or in space.
It is infinite in space.
In space, and it keep also infinite in space. The whole idea there, how close the points was to each other, but still infinite back
infinite
then, and
number
infinite
of points
now.
and infinite extent in space.
That's very interesting, because that's people usually tend to imagine those kind of early universe as a very tiny space.
Like an explosion, like a firecracker. But that's not what's happening. Space was always infinite in this model that best fits the data now, the simplest model. And it gets bigger and bigger. Every one of those points, infinite number of points, moves apart further and further.
That's very interesting. And also we did talk a little bit about the anisotropy, but I think I want to emphasize more on it before we go to the idea of dark matter and dark energy. It's like cosmologists usually say that when you look to our universe close, you find it anisotropic. And if you look to a large picture of it, it will be isotropic. But what do you guys mean by that?
Okay, so if you think about this room, I'm here and you're there. And when we look up, if we look up, we don't see another one of you up there, another one of me up there. So it looks different in different directions. If I look that way, it doesn't look the same as when I look at you. And you can think about this campus. So I don't know how high the tallest building is, but there was a radio tower or something next to that thing that looked like a couple of 100 feet high. So if you climb to the top and look around, you'll see different buildings in different directions. And if you go up 50 miles or so, and you look to the south and to the east, you're going to see the Gulf of Mexico. And if you look inland, you're not going to see the Gulf of Mexico, so you're going to see land. And it just looks different in different directions. So when something looks different in different directions, one says it's anisotropic. And when it looks the same in different directions, you say it's isotropic. And you can go out to larger scales, like the solar system, and you look in one direction, you see this big star, the nearby star called the sun, and you look in any other direction, you don't see an equally big star. And just to give you some idea of the scale, if you're traveling at the speed of light, it takes you about 500 seconds to get from the Earth to the sun. And you can compare that to the Earth and Moon distance. It takes like maybe a second and a third to get from the Earth to the Moon. And if you want to go across the whole of the Milky Way, it takes 160,000 years if you travel at the speed of light. And so even on the scale of the Milky Way, if you look in one direction, you see towards the center, and there's the bulge there, and in that bulge, there's a big black hole. And you look in the opposite direction, you don't see anything. I mean, you see a few stars, but you don't see the thousands of stars you see when you're looking towards the center. So it's anisotropic. But when you get out to scale, so that's like hundreds of thousands of light years. And you can even look towards Andromeda, which is another galaxy, and it's gravitationally bound to us. And that's about 2.5 million light years away. And looking towards Andromeda, you see this galaxy 2.5 million light years away. You look in any other direction, you don't see an equally big galaxy. But once you start getting to tens of millions or 50 million light years, you look in different directions, you don't see that many different things. They look roughly the same. And so on large scales, distribution of stuff in space is isotropic. It's the same no matter what direction you look in. But when you're looking at stuff in our universe on smaller scales, it looks different in different directions. And this Einstein's picture of new space being created and spreading itself out only applies on scales of 50, 100 million light years and larger, but not on the scale of the Milky Way, not on the scale of Earth. The Earth's not expanding, and the Milky Way is not expanding.
You're using the word that's new space being created. I thought that's a bit hard to imagine, because usually, I remember when I read about the expansion of the universe, always scientists say the universe expands into itself.
Yeah.
But does this mean if we calculate the volume, I don't know if we can do that, does the volume increase, meaning that
it's infinite and it gets bigger?
Yeah, it's still infinite. It's still infinite.
So yeah, we're having this discussion in English, and so all of our intuition for physics, I mean, if you haven't taken more advanced classes and done experiments and stuff, all of that intuition sort of comes from our direct senses. So you need to know Newtonian physics to survive, and so you understand that, because you can't walk otherwise. And even though you don't do this intellectually by writing down F equal to ma and then figuring out how to walk, you've mastered Newtonian physics. And you master it when you're a toddler, because a toddler has to crawl and has to walk. And so there's certain length scales you can directly access with your senses. I mean, probably the finest thing you can feel is a strand of hair, and that's maybe 10 to the minus 4 meters in width. And maybe you can directly access 1,000 kilometers or 10,000 kilometers, which is 10 to the 7 or 10 to the 8 meters. But those are the scales on which Newtonian physics applies, and so you directly get all your physical intuition from that.
Basically, our common sense is not...
Yeah, that's what you call common sense, but it's Newtonian, it's your understanding of Newtonian physics. And if you want to see what's happening on atomic scales, you're not going to be reaching in there and touching atoms with your fingers. So what you're going to be doing is you're going to take an accelerator, particle accelerator, and maybe hitting the atom with some other particle and seeing how that particle bounces off and seeing whether it emits light. And so all of that, you're going to have these CCD detectors to get the light, and you'll store that as an electronic file in a computer. And then you'll build a mathematical model. You'll take Schrodinger's equation and solve it and try to predict what light you should see from what atom. And you're not using your direct intuition. And without doing that, you won't build up your intuition.
Basically, once we live the short scale that we live in, our intuition doesn't mean much at that point. Neither on the big scale or small scale.
Yeah, it doesn't mean much for what's happening on huger scales or much smaller scales. And there's a number of really interesting videos on this. So one's called The Powers of 10 by the Eames brothers. And I think that's from the 1970s or so. That's EAMES. And the American Museum of Natural History in New York has an updated version in the last 15, 20 years.
Yeah, that's very interesting.
It's well worth looking at. Maybe you can put a link in there.
That's what will happen. I think we covered a lot about our universe today. Like we did talk about the beginning, the expansion, the isotropy or anisotropy. And however, that brings me to the important part, which is your current work. You're working on the dynamical expansion of our universe. Basically, we say we had two unknown variables. I wouldn't say variables, but quantities that we don't know One of them is the dark matter, and this other one is the dark energy.
Yeah.
So first, if you would like to tell us what both are, why the both are called dark, why one is matter, one is energy.
Yeah. So maybe I'll take a little bit of a digression, and we can kind of think about our solar system a little bit. So the planet closest to the sun is Mercury, and until a little while ago, the planet furthest from the sun was Pluto.
Not anymore.
Since Pluto was discovered by Tomball, who's from Kansas, I'll use that as an illustration.
Okay.
So Pluto is really, really far away, and Mercury is really close. And what's causing that motion of Pluto and Mercury is the sun's gravitational field. And we can discuss this in terms of Newton's law of gravity, his inverse square law. So he said if you have two masses, they're going to pull towards each other because of the gravitational field. And that strength of the field is dependent on both their masses. You take the product of their masses and you multiply by Newton's big G, his gravitational constant. And it's inversely proportional to the square of the distance between them. So you double the distance, then that force goes down by a factor of 4, which is 2 squared. If you triple the distance, it goes down by a factor of 9, which is 3 squared. And since the sun is producing most of that gravitational field and Mercury is really close by compared to Pluto, Pluto feels a much weaker gravitational field. So Mercury wants to keep going straight, but the sun's going to bend it, and it's going to bend it much more effectively than it bends Pluto's orbit. And so Mercury goes around in 88 days, and Pluto takes 220 years to go around the sun. And so if you make a plot of the speed of the planets against their distance, it'll drop off like this. So the ones closer to the sun are going much faster and it drops off like this. And then you go and look at a similar system, at least in terms of geometry. You look at the Milky Way. It's got stars going around the center in this thing called the disk. And you can measure how fast those stars are moving. And you find when you make this plot that for the solar system does this, for the Milky Way it goes up and then it flattens out and does that. And so that's telling you there's something very strange happening. There's got to be something that's creating a stronger gravitational field at the edge. I mean, if you suddenly saw Pluto start going much, much faster, it's feeling something, a much stronger gravitational field than just the mass in the sun. And so one way to do that is to increase the mass. And so what people think is happening is that there's a lot of mass in the disk of our Milky Way and even beyond the disk of the Milky Way. But when we go and count up the mass in stars, we don't see the amount of mass we need to produce that gravitational field to make those stars go that fast. So because we're seeing the motion and we think Newton's laws are correct, and then we're forced to this conclusion that there's some matter there that produces this mass that's producing the gravitational field, but it cannot be producing the light because it's not shining and we're not seeing it. And that's what dark matter is. And we know how fast these stars are moving. So it's a few hundred kilometers a second. And compared to the speed of light, that's very, very small. So this motion is called non-relativistic. And a less technical term for it is called cold. So it's cold motion or cold dark matter. And that's what dark matter is. We're seeing its gravitational field make the shiny stuff move faster than it would move in the absence of dark matter. And that's about 5 times as common as the amount of atoms and molecules out there. And the atoms and molecules make up about 5% of the energy of the universe now, and the dark matter makes up 25%. And this other thing called the dark energy it's even stranger, and it doesn't do much on the scale of our galaxy, but it starts becoming more and more important on scales of tens to hundreds of millions of light years. And what it does, I can tell you, well, maybe I should tell you why it was introduced So people, if you kind of think about gravity and you have a whole bunch of masses, they want to pull towards each other. And so if you think about Einstein's space creation process and a whole bunch of masses there, the masses will obey Newton's law if they're close enough, and they'll pull together. And so if you make them heavier and heavier and heavier, they're going to try to overwhelm Einstein's space creation process. So if you think about the Big Bang and just a whole bunch of masses there, you start the expansion, things start moving apart. But because the masses want to attract towards each other, they're going to try to stop the space creation process. And so the expansion should start and should go on and should slow down and slow down and slow down. Or if you want to think of this in terms of a person driving a car, she can start from the curb and turn it on and hit the gas pedal and start moving. And then you want to know whether she's speeding up or slowing down. And if she hits the brake, she'll slow down, but she'll still keep moving forward until she eventually stops. If she hits the gas, she'll just keep going faster and faster. So the slowing down is decelerating, and the speeding up is accelerating. And in Newton's picture, gravity should be causing masses. If you have more masses, it'll cause deceleration. And so you're happy and you go tell your astronomer friends that Newton would tell you that if you had a lot of mass, that the expansion of the universe would decelerate. And so they go out there and they measure and they discover that it's actually accelerating. Yeah. So then you can say that our model of gravity, even Newton's model or Einstein's model with a lot of mass, is incorrect, and you just throw it away and you say there's no problem. But if you're a little bit more conservative and you realize that gravity, Einstein's general relativity, explains black holes very well, and it explains gravitational waves very well, and so it has some great successes, and you're a little bit more conservative and you don't want to throw away general relativity. The other thing you could do is that general relativity doesn't tell you what the matter content is. It tells you how gravity responds to matter.
Exactly.
And so you can introduce hypothetical substances into general relativity and see what it does. And so one hypothetical substance people try to introduce is called Einstein's cosmological constant. And I mean, this wasn't hypothetical when he introduced it, but he made, he wasn't aware of the observations, but we can come back to that if you want to talk about it. Yeah, but sure. So you can introduce this thing called the cosmological constant, and it's a kind of energy that's the same everywhere in space and doesn't change in time. And what it does when you have general relativity and a cosmological constant is that it makes the expansion accelerate. And so when these guys discovered this accelerated expansion, people said, maybe you're just seeing a cosmological constant. And excuse me for a second. And a cosmological constant is really strange. It's this constant that's the same no matter where you are in space and no matter what time it is. And that's very difficult to reconcile with other parts of physics that are based on these field theories, whose fields change depending on where you are in space and where you are in time. And so the natural thing to try to do is to have something like a cosmological constant be replaced by a field that varies in space and time.
Which is what you guys doing.
Yeah, so that's what we did in the 1980s, because it was getting to be pretty clear then that something like a cosmological constant or curved geometry was more accurately describing the real universe than without a cosmological constant or without curvature. And so we introduced a field for it, and that's what dark energy is. It varies depending on where you are in space and time, but it varies very, very gradually in time, and it varies even less in space. So it's almost a cosmological constant, but it still varies both in time and space. And the hope is it's a scalar field and that it can be something similar to the Higgs field or the field that drives inflation.
So basically, instead of having one value for the constant, it become a dynamical constant that will change based on where you are in that field, in that scalar field.
Yeah, and then you build a more sophisticated mathematical model. You characterize it in terms of what's called a potential or a potential energy, a potential energy density, and that might have one parameter or two parameters, but it allows the field to vary in time and space. So you're not introducing an infinite number of new things, but you're just introducing one or two new variables.
And where we are in terms of observation from that new model?
So the observations are difficult now. So it's not going to make predictions that are significantly different from a cosmological constant. What it's going to predict is it's going to predict a slightly different amount of bumpiness in the cosmic microwave background. And it's going to predict a slightly different expansion rate for the universe. And the precision of our measurements are not at the point where you can distinguish between the prediction of that and a cosmological constant. So we know if it's dark energy, the dark energy density cannot change radically in time. It's got to be gradual. And it cannot change rapidly as you go and look at different spatial length scales. It's got to be gradual. But the hope is that in the next 5, 10, 15 years with these new experiments, one's called DESI, that's a dark energy spectroscopic instrument, that's going to try to measure the expansion rate over a lot of the history of the universe, at least maybe half of the history or more than that, maybe 3/4 of the history going back to when the universe was a few billion years old. And maybe that'll be precise enough to distinguish between whether it's a constant cosmological constant or of time-varying dark energy density.
That's very interesting, actually. That one of the, I think it was a lecture I attended at some point, might be related. It was speaking about the Hubble constant tension or the different observation. That will be related.
That's partially related. So the expansion rate of the universe is how the universe expands as a function of different times. And the expansion rate at the present time is called the Hubble constant. So if you go back to the early universe, you have a Hubble law, but the constant of proportionality won't be the same value it is now. So right now, there's this thing called the Hubble tension, which is the difference between some different measurements of the Hubble constant. So there's a number of different ways to measure the Hubble constant. And the Hubble constant is a very interesting parameter in science. There's probably been roughly 800 or 900 measurements of it. It's probably been the most measured parameter ever since Hubble introduced it in 1929, so almost a century ago. And for a long time, I mean, Hubble and his collaborators, Thuman and others, were finding a slower expansion rate, maybe almost by a factor of 2 compared to what another famous astronomer, de Vecula, was finding. He was finding a Hubble constant twice as large almost. And it turned out that was because both of them didn't have a very accurate handle on the systematic errors. And that difference between measured Hubble constant values has continued to the present day, but it's no longer a factor of 2. So the Hubble constant is just the expansion rate, but it's got strange units because of astronomy conventions. And so what it tells you is that each time you go a megaparsec in distance, then you increase things by a kilometer a second. And so the Hubble constant now is roughly about 70 kilometers per second per megaparsec. And the discrepancies are roughly from 68 or so and 73. But the thing is, both these measurements have extremely small error bars. So the 68 one is plus minus, well, maybe it's somewhere around 68 and a half or so. And it's maybe
So
plus
the question
minus
will
half.
be, is it an actual physics or just
Right.
an systematic uncertainty that need to be considered?
Yeah. So the 68 one comes from fitting the cosmic microwave background. And the measurements there are much cleaner, but you've got to assume a cosmological model to extract the Hubble constant. And the 73 one comes from certain one or two groups where they use these pulsating stars called Cepheid variable stars to calibrate type 1a supernovae. And so it depends on how you model these pulsating stars, and that's where all the messy astrophysics is. And so it depends on that. And so it's unclear. I think there's that the model we have for the current universe, the lambda CDM model, is good, and
a lot to be done.
It can't be ruled out by these differences in measurements, and that it's probably more related to not quite understanding how to do the measurements that accurately, but we'll see.
I think that brings us actually to the end of the podcast. I think it was very, very nice and knowledgeable one. I think we talk about the universe, about expansion, space expansion, what is dark matter, dark energy, what's isotropy and anisotropy. And I think it's we'll leave that to the audience to hopefully learn more. We will add some links to your previous talks, and I hope they enjoy it. And thank you so much for being a part of my show.
Thank you for having me. It's a great pleasure.
It's a pleasure to me. See you hopefully next time with more information.
Soon, hopefully.
Thank you so much.
Thank you.
Okay, bye-bye everyone. Thank you.
Thanks.